Hello, everyone. My name is Peng Zhang. I am from Rutgers University. Today, I will present our paper, Hardness Results for Weaver's Discrepancy Problem. This is a joint work with Daniel Spielman from Yale University. What is discrepancy? If you look at this word in a dictionary, then you will find that discrepancy means a difference between two things that should be the same. In 2004, Weaver defined this discrepancy problem. Suppose we are given n vectors, v1 dot dot vn. We want to find signs xi dot dot xn, each with value -1 or 1, to minimize the spectral norm of the sum of xi vi transpose. What is the spectral norm of a matrix? Here we consider a matrix A. We define the spectral norm of matrix A to be the maximum Euclidean norm of A times vector V among all the vectors V with Euclidean norm 1. And this is a visualization for a 2 by 2 dimensional symmetric matrix A. This blue circle contains all the vectors V with Euclidean norm 1. If we multiply matrix A to all these vectors, we get this blue ellipsoid. The length of this longer semi-axis is the spectral norm of this matrix A. In particular, if matrix A is a diagonal matrix, then the spectral norm of A is the maximum diagonal entry in absolute value. Weaver conjectured that there exist two absolute constants, alpha and beta. Alpha is greater than 0 and beta is smaller than 1, such that for any vectors, v1 dot dot vn, satisfying the following two conditions. So the first condition is that every vi has a squared Euclidean norm at most alpha. And the second condition is that the sum of vi transpose equals the identity matrix. There exists signs x1 dot dot xn, each with value -1 or 1, such that the spectral norm of the sum of xi vi transpose is upper bounded by the constant beta. So here, these two constants, alpha and beta, are independent of the number of vectors and also the dimensions of these vectors. So roughly speaking, if we have n vectors that are in the isotropic position, and there is no vector with a large Euclidean norm, then there exists a partition of all these vectors into two groups, so that the two groups are similar in a spectral sense. Weaver's conjecture implies a positive answer to the famous Cadison-Singer problem. In 2015, Marcus, Spielman, and Srivastava confirmed Weaver's conjecture, with beta being the square root of 8 times alpha plus 2 times alpha. And later, this constant beta has been improved to the square root of 8 times alpha. However, both these two proofs are non-constructive, and until now, no polynomial time algorithms are known for constructing signs x1 dot dot xn that match the bound by Marcus, Spielman, and Srivastava. The currently best known algorithm has runtime 2 to the power n to the power 1/3 over alpha. Okay, in this paper, we prove two hardness results for Weaver's discrepancy problem. To simplify our theorem statement, let me first introduce some notations. We say vectors v1 dot dot vn are alpha waiver if these vectors satisfy the following two conditions. So first, the sum of this vi transpose equals the identity matrix. And second, every vi has a squared Euclidean norm at most alpha. And we define Weaver's discrepancy for vectors v1 dot dot vn to be the minimum spectral norm of the sum of xi vi transpose, where the minimum is taken over all the possible signs for x1 dot dot xn. So under these notations, Weaver's conjecture states that there exist absolute constants alpha and beta, such that any list of alpha Weaver vectors has Weaver discrepancy at most beta. Our first result concerns alpha being 1/4. We show that for 1/4 Weaver vectors, it is NP-hard to distinguish between these vectors with discrepancy 0 and those with discrepancy at least 1/4. This result was independently discovered by Jordan, McGregor, and Sun recently. Our second result concerns more general alpha. So for any alpha that is not too small, and for any alpha Weaver vectors, it is NP-hard to distinguish between vectors with discrepancy 0 and those vectors with discrepancy at least root alpha times some constant. Okay, I want to point out that our results do not answer the question whether there exists a polynomial time algorithm for constructing signs x1 dot dot xn that match the bound by Marcus, Spielmann, and Srivastava absolute constant. Our proof is inspired by the proof by Cherika, Newman, and Nikolov for some Hardness results for another notion of discrepancy. Okay, our proof builds on reductions from 2-2 set splitting problem. A 2-2 set splitting problem instance is a family of sets S1 dot dot Sm. Each is a subset of elements from 1 to n, and each has exactly 4 distinct elements. An assignment for the elements is a list of n numbers, z1 dot dot zn, each with value 1 or -1. We say an assignment satisfies a set Sj if the sum of the values of the elements in Sj equals 0. We say an element satisfies the instance if it satisfies all the sets in this instance. And we say an instance is satisfiable if there exists an assignment that satisfies this instance. And here is a simple example for 2-2 set splitting problem. We have 15 elements, and we have 4 blue sets and 3 green sets. So in total, we have 7 sets. And here is an assignment for all these 15 elements. And we can actually check that this assignment satisfies this instance. In 2004, Guruswamy showed that for 2-2 set splitting instances, it's NP-hard to distinguish between satisfiable instances and unsatisfiable instances. For our reduction, we need a more restricted version of 2-2 set splitting instances. We call it a 3-1-2-2 set splitting problem. It is a 2-2 set splitting problem that satisfies two additional conditions. So first, we require that every element appears in at most 3 sets. And second, we require that every 2 sets share at most 1 element. We can show that Guru-Swami's hardness result actually holds for this special 3-1-2-2 set splitting problem. And here is a proof. For any 2-2 set splitting instance, we can convert it to a 3-1-2-2 set splitting instance by using this gadget that forces 2 elements to be equal. Okay, first we can check that this assignment satisfies all the 3 sets in this gadget. And in this assignment, element A equals element B. And next, we claim that for any assignment that satisfies all these 7 sets, we must have that A equals B. We first look at all these 3 green sets. If all these 3 green sets are satisfied, then half of the Y elements must be assigned 1, and half of the Y elements must be assigned -1. Then we look at all the 4 blue sets. If all these 4 blue sets are satisfied, then element A must be equal to element B. Okay. There is actually a simple reduction if we only consider sums of arbitrary matrices instead of sums of rank 1 matrices. Given a 3-1-2-2 set splitting instance, for each element I, we construct a diagonal matrix Di. The jth row and the jth column of Di corresponds to the set Sj in this set splitting instance. We set the jth diagonal of Di to be 1/4 if element I is in set Sj. And we set this number to be 0 otherwise. Okay, we can check that the sum of this diagonal matrices Di equals the identity matrix. This is because in the 2-2 set splitting instance, each element appears in exactly 4 each set has exactly 4 distinct elements. Okay, for any assignment Z1 dot dot Zn, if we look at the matrix, the sum of Zidi, then the jth entry of this matrix is actually the sum of the elements in set Sj. Okay, if the 2-2 set splitting instance is a satisfiable instance, then there exists Z1 dot dot Zn, each with values 1 or -1, such that the sum of Zidi equals 0. Well, if this 2-2 set splitting instance is an unsatisfiable instance, then for any Z1 dot dot Zn with values 1 or -1, there must exist a set Sj such that the sum of the elements in Sj has an absolute value at least 2. So this means that the jth entry of the sum of this means that the jth diagonal of the sum of Zidi have absolute value at least 1 or 2. Okay, to convert these matrices DI to rank 1 matrices. We write each DI as a sum of orthogonal vectors. Here we explicitly construct 3 vectors, Q1, Q2, and Q3, each in 3 dimensions. We observe that the sum of Q1, Q1 transpose, Q2, Q2 transpose, and Q3, Q3 transpose equals the identity matrix. In addition, we can check that for every signs Z1, Z2, Z3 that are not all equal, and for every diagonal matrix X, the sum of X and the sum of Zi, Qi, Qi transpose has a spectral norm greater than or equal to 1. So this means that if we want a smaller spectral norm, we must have all these 3 signs, Z1, Z2, Z3, to be all equal. Okay, here is our construction. For simplicity, we assume that in the 2-2 set splitting instance, every element appears in exactly 3 sets. Otherwise, we will add some dummy set and dummy elements. Okay, for each element I, we construct 3 vectors, Qi1, Qi2, and Qi3. For each Qih, we set the 3 coordinates that correspond to the 3 sets containing element I to be half times Qh, and we set all the other coordinates to be 0. Okay, we can check that the sum of Qi1, Qi1 transpose, Qi2, Qi2 transpose, and Qi3, Qi3 transpose equals the diagonal matrix Di. In addition, we can check that these vectors Qih for I goes from 1 to n and h goes from 1 to 3 are at least a 1/4 Weaver vectors. Okay, and here is our proof. If the 2-2 set splitting instance is a satisfiable instance, then we will construct signs xih for every I and h, such that Weaver's discrepancy under this signs is 0. Okay, suppose the 2-2 set splitting instance is satisfied by an assignment z1 ... each with the values 1 or -1. Then we set every xih to be zi. And then Weaver's discrepancy, the spectral norm of the sum of xih, qih transpose equals the spectral norm of the sum of zidi, which is 0, because the 2-2 set splitting instance is a satisfiable instance. Well, if this the 2-2 set splitting instance is an unsatisfiable instance, then we claim that any signs xih must have Weaver's discrepancy at least 1/4. Okay, there are 2 cases that we need to consider. In the first case, for every I, the 3 signs xi1, xi2, xi3 are all equal, and we assume that they all equal to some number zi. Then the discrepancy is the spectral norm of the sum of zidi, which is greater than 1/2. Okay, in the second case, there exists some I such that all these 3 signs xi1, xi2, and xi3 are not all equal. Okay, then we look at the submatrix of the sum of xih, qih transpose restricted to the sets that contain element I. And this submatrix is actually a 3 by 3 dimensional matrix. It can be written as a diagonal matrix plus the sum of XIH, QH, QH transpose. Okay, this is because we assume that in the 2-2 set splitting instance, every 2 sets share at most one element. Okay, here we apply this lemma. And we know that the spectral norm of this submatrix is at least 1/4. So the spectral norm of the whole matrix is at least 1/4. And since it's NP hard to distinguish between satisfiable 2-2 set splitting instances and unsatisfiable instances, it is NP hard to distinguish between 1/4 waiver vectors with discrepancy 0 and 1/4 waiver vectors with discrepancy at least 1/4. So this proves our theorem 1. Okay, for our theorem 2 regarding general alpha, we need a stronger hardness result for 2-2 set splitting problem. Let me first introduce one more definition. We say a 2-2 set splitting instance is gamma unsatisfiable if for every assignment Z1 dot Zn, at least a gamma fraction of the sets are unsatisfied. Guruswamy showed that for any positive epsilon, there exists some constant b such that for 2-2 set splitting instances in which each element appears in at most b sets, it's NP hard to distinguish between satisfiable instances and instances that are 1/12 minus epsilon unsatisfiable. A similar hardness result actually holds for the special 3-1 2-2 set splitting problem. There exists a constant gamma such that for 3-1 2-2 set splitting instances, it's NP hard to distinguish between satisfiable instances and gamma unsatisfiable instances. Okay, here is a sketch for our proof. Our construction has 2 steps. The first step is similar to our construction for alpha being 1/4. We write each di as a sum of orthogonal vectors, and we get 1/4 waiver vectors, v1, v2, and so on. We want that when the 3-1 2-2 set splitting instance is gamma unsatisfiable, for any signs, x1, x2, and so on, if we look at the matrix, the sum of xi, vi, vi transpose, a constant fraction of the diagonals of this matrix have a large absolute value. Our second step constructs alpha waiver vectors based on these vectors v1, v2, and so on. We multiply each vi with a fat matrix F, and we get a list of new vectors, u1, u2, and so on. We want these vectors to be alpha waiver. We also want that when at least a constant fraction of the diagonals of the sum of xi, vi, vi transpose have large absolute value, this new matrix, the sum of xi, ui, ui transpose, has a spectral norm, which is greater than root alpha times some constant. We achieve this by constructing F using the edge vertex adjacency matrix of a complete graph. Okay, so this is all for the talk. Thank you for watching the video.